In this video, I'm going to show you how techniques for finding the maximum minimum of a function using derivatives can be used to figure out how to minimize inventory costs. So in this problem, we have a company that is expecting to sell 120 units per year of a certain product, a product that they have to order. So they have to take into account for their inventory costs. Once they get the product in, how much it costs to store the units of this product. So they estimate that their storage cost is $2.40 to store a unit for a full year. Now, we don't expect once the product comes in that those units are going to sit around in their warehouse for that full year, but we're going to use this baseline of $2.40 per unit per year to try to estimate storage cost overall for all the units that they order. When they do reorder units after they run out, there's a fixed cost of $9 per order, and on top of that, variable cost of 80 cents per unit included in the order. So there are going to be 120 units ordered throughout the course of the year, but the question is, how's it going to be broken up into orders? Are they going to place 6 orders per year and 20 units per order? Or is it going to be, for instance, 40 units broken over 3 orders per year? How's it going to break down like that? Or the extreme case, where they place only 1 order for all 120 units, or the other extreme, 120 orders, 1 unit each. So for however many units there are per order, which is the lot size, and then the number of units per order would just be 120 divided by that, so the total number of units is 120. What is the right combination of lot size and units per lot that it's going to give them 120 units no matter what, but will result in the minimum cost? Because if they order more units up front, so in other words, a larger lot size but fewer orders, if say they order all 120 units at the beginning of the year, it takes a while to sell those units, so they're incurring increased storage costs. On the other hand, if they decide to place small orders and order more frequently, this part of the cost is not going to be affected. You're spending 80 cents per unit no matter what. But the fixed cost of an order, $9 for instance, for shipping or processing, that's going to increase. So because of this cost, they have a reason to place fewer orders. Because of this factor, they have a reason to place more orders that are smaller. So we have to find the right way to balance these competing criteria. So the question is, what is the lot size and number of orders per year, the product of which will be 120, that will minimize inventory costs? So we're going to express the inventory cost as a function of these 2 variables, the lot size and the number of orders per year. So I'm going to refer to the lot size as X. So how many units there are in a single order. And then I'll use Y to refer to the number of orders per year. So we know that X times Y is equal to 120. So that's going to help us in just a little bit. But we want to be able to express the total cost, inventory cost, in terms of these 2 variables. Okay. Now we're accustomed to working with functions of 1 variable, but it's easier to come up with a function in terms of both variables, and then we'll use this to eliminate one of the variables and use calculus techniques from there. Okay, so first for the storage cost, it's going to be $2.40 per unit per year, but how many units are really going to sit in the warehouse during a full year? The way we're going to estimate that is we're going to use half of the lot size, X over 2. And the reasoning behind that is So once you place your order and your units have arrived, if we assume that the units are sold at a uniform rate, so like on a regular pattern, like every few days or so, a unit is sold. So in fact, that's what happening here. Over the course of 365 days, we're having roughly one unit sell every 3 days. Then, on average, you have half the lot size that is sitting in your warehouse. If you assume that we have this uniform rate of selling, also if we assume that once the units from a particular lot are sold, then you immediately reorder and get those units in quickly. So you have a steady flow of units coming in, but therefore you have, on average, half a lot sitting around per year. So this is the cost just from storage. And then the cost from reordering is going to be, for each order that you place, and Y is the number of orders per year, it's going to be 9 plus 0.8 times X. So this is our total cost. Okay. So now I'm going to simplify this a little bit. So 240 over 2 is 1, or 2.4 divided by 2 is 1.2 X plus 9Y plus 0.8 XY. Now, I want to express this as a function of only X, the lot size. So to do that, I can use the fact that X times Y is equal to 120. So this right here, X times Y, that is 120. And then Y is equal to 120 divided by X. So I can fill that in right here. So taking all this into account, my cost expressed as a function of only X, only one variable, is going to be still 1.2X plus 9 times 120 over X, so that's 1,080 divided by X, plus 0.8 times 120, which is 96. Okay, so that is my inventory cost as a function of the lot size, the number of units per order. So I want to find a value of X that gives me a minimum value of this function. So to find a minimum of my cost function, my inventory cost function, C of X, I take the derivative. So C prime of X is going to be, so we have 1.2 times X, so the derivative of that is just going to be 1.2. And then I have 1,080 times the derivative of 1 over X. Well, 1 over X is the same as X to the minus 1. So to take the derivative, that would be minus X to the minus 2. So the derivative of 1 over X, this is something that's good to remember, is minus X to the minus 2, or minus 1 over X squared. This comes up often enough in problems. That's a prime, by the way. Okay. So the derivative of 1 over X is minus 1 over X squared. So I've used that here. And then the derivative of 96 is 0, so it's a constant. So this is my entire derivative. So now I can rewrite this as 1.2 minus 1,080 over X squared. Okay. Now, I will set this equal to 0 to find the critical point, which it could be a local maximum or local minimum. So if I move the second term to the other side, I get 1.2 is equal to 1,080 over X squared. And then I multiply both sides by X squared, so 1.2 X squared is 1,080. And then I divide both sides by 1.2. So 1,080 divided by 1.2, you can use your calculator if you like, but what you get is 900. So now you take the square root of both sides, Now, the number of units per order, of course, is going to be positive, so we just want the positive square root, and x is equal to 30. So your lot size is 30, and since you expect to sell 120 units per year, so y is 120 divided by 30, which is 4. So you're going to place 4 orders per year at 30 units per order, and that will lead to the minimum inventory cost. So, so whatever cost you incur from storage and whatever cost you incur from reordering is balanced out in the best way possible.